In this lecture, we will discuss continuous functions, but specializing to the case of the metric topologies on metric spaces. So this will be closest to the usual definition of continuous functions in terms of the calculus of real variables. So recall from calculus, those of you who have seen it. So we have two definitions of continuity of functions, real valued functions on R. So one is the so-called Epsilon Delta definition of continuity, Epsilon Delta definition, and the other one is the convergent sequence, or rather limits. Let me write it as limits, in terms of limits. So we will shortly see the Epsilon Delta definition of continuity, not just for R but for any metric space. But for the second one, I can write it down quickly. It just means that for any x in R and any sequence xn such that the limit as n tends to infinity of xn equals x, we have the limit of n tends to infinity, f of xn is equal to f of x. So in terms of limits, we see that this is the same as interchanging of the limit operation and the function. So interchanging property, because on the right hand side we can write this as so the limit n tends to infinity f of xn, this is the left hand side. The right hand side is f of x, but this is nothing but f of limit xn as n tends to infinity. So we have interchanged the order of taking the limit operation and taking the function operation. Now for those of you who do not know what a limit is, we will see very shortly what it means for a limit of this sequence xn to converge to x for any metric space, and in fact for any topological space. So let us start with the Epsilon Delta definition of continuity for metric spaces, and after that we will take on the definition in terms of limits or convergence of sequences. Now for the Epsilon Delta definition of continuity, we take two metric spaces x dx and y dy. So dx and dy are metric functions on x and y, and both x and y are given the metric topologies with respect to these two metric functions. So what is the Epsilon Delta definition of continuous functions? So let f be a function from x to y, be a function, then f is called continuous with respect to the metric topologies on x and y if and only if. So this is a shorthand for if and only if and only if we have for each x in x and epsilon greater than 0, there exists a delta greater than 0 such that whenever x prime lies in the metric ball with center x and radius delta, this implies that f of x prime belongs to the metric ball in y with center f of x and radius epsilon. So this is the Epsilon Delta definition of continuous functions for metric spaces, and in the case where x equals y equals r, and dx and dy are the Euclidean distance function, then this condition reads as follows. So you have x minus x prime less than delta implies that fx minus fx prime is less than epsilon. So this might be familiar to you from calculus courses, and this is the definition we gave for metric spaces is an immediate generalization of this definition. So now the first thing to show is that the epsilon delta definition of continuous functions for metric spaces is equivalent to the definition of continuous functions we gave for arbitrary topological spaces in terms of open sets. So here's the theorem. So it states that if f is a function between two metric spaces as we have described above, then f is continuous with respect to this epsilon delta definition if and only if f is continuous with the open set definition for arbitrary topological spaces that we have seen before. So let us see a proof of this theorem. So let us look at the proof. So for the forward implication, so we suppose that f is continuous with the epsilon delta definition, and we want to show that f is continuous with respect to the open set definition. And for this we will use part 3 of the theorem 3.1 in lecture 3 that we proved, which was that f is continuous if and only if for each x in X and any neighborhood of fx, say v, there exists a neighborhood u of x such that f of u is a subset of v. So let us see how we can use this result to prove the forward implication. So let x be in X and v be a neighborhood of fx. Now since v is open, this implies that there exists a number epsilon greater than 0 such that the metric ball in Y of with center fx and radius epsilon is a subset of V, just because these kinds of sets are the basic sets for the metric topology. So now by the hypothesis which is the epsilon delta continuity of f, there exists a delta greater than 0 for this given x and this given epsilon. There exists a delta greater than 0 such that we have x prime in b dx x delta implies fx prime belongs to b dy fx epsilon. And notice that this is equivalent to saying that f of b dx x delta is a subset of b dy f of fx of fx and with radius epsilon. Now this set is a subset of V, and so if we choose our U to be the set with center, the Euclidean ball with center x and radius delta, then we have found such a U for our use of this part 3 of theorem 3.1, and this implies that f is continuous. So we see that if f is epsilon delta continuous, then f is continuous in the abstract sense, meaning that it is continuous in the open set definition. Now let us look at the reverse implication. So suppose that f is continuous with respect to the open set definition, and now we can again use part part 3 of this theorem 3.1 as we described above. So for this we have to show that given x in x and epsilon greater than 0, there exists delta greater than 0 such that x prime in b dx x delta implies fx prime in b dy fx epsilon, right? So how do we show this? So we know that f is continuous with the open set definition. Now again using part 3 of theorem 3.1 as above. So now take V to be this set B dy fx with radius epsilon. Then this implies that there exists, because f is continuous, there exists an open set U, a neighborhood of x, such that f of u is a subset of V. Now because U is open, this implies that there exists a number delta greater than 0 such that b dx of x delta is a subset of U, and this means that f of b dx x delta is also a subset of V, and this is what we want to show. So this is equivalent to saying that x prime belongs to b dx x delta implies fx prime belongs to b dy fx epsilon. So we have shown the equivalence of these two definitions for the case of metric spaces. Now we come to a very important topic in topology as well as in real analysis and complex analysis, which is that of convergence of sequences. So what is a sequence first of all? So let X be a topological space. Then a sequence in X, we write it as denoted by xn, n in the natural numbers. So it is, you can view it as a collection of one-point sets indexed by the natural numbers. So is a collection of singleton subsets of X indexed by the natural numbers. You can also view it alternatively. A sequence is a function f from n to x. So we have always seen that whenever you have these kinds of collection of points which can be written in terms of coordinates and indexed by the natural numbers or indexed by some finite set, then you can write it as a function, and this is exactly what is happening here as well. So it can be seen as a sequence. A sequence can be seen as a function from the natural numbers to x, or a sequence is an element of the infinite Cartesian product of xn with xn equals to x for all n. Okay, because each function is an element of this Cartesian product, so a sequence can also be viewed as an element of the infinite Cartesian product. But we will just keep this in mind, and we just view a sequence as a collection of singleton subsets of X which are indexed by the natural numbers. So what does it mean for a sequence to converge? Convergence of sequences. So what does it mean for a sequence to converge? So for example, take the sequence xn to be 1 by n, where x is now the set of real numbers with the standard topology. And we have seen that 0 is a limit point of this set of numbers 1 by n, and as n increases, the points go closer and closer to the point 0, never reaching it but getting arbitrarily closer to the point 0. So in this case we say that xn converges to 0, xn converges to 0, or that the limit of xn as n tends to infinity is equal to 0. So I haven't given a formal definition yet, but just to give you an idea of the convergence, when a sequence of points goes closer and closer to a certain point, or it could be many different points as well, as we will see, then we say that the sequence converges to that point. And now let us see a formal definition of the convergence of sequences. So a sequence xn n in n converges to a point x in x if for each neighborhood u of x there exists a natural number capital N such that xn belongs to u for all n greater than or equal to this capital N. So it means that after some time, it does not matter which neighborhood you choose, after a finite number of terms in the sequence, so here this is the capital N, we have all the rest of the points in the sequence must lie in this neighborhood. So for 0, here we have 0, and let us say we choose a neighborhood of length, let us say 0.1, okay, minus 0.1 to 0.1, and then the sequence of functions 1 over n converges to 0 here, since for r equals 0.1 the so we have the capital number N here is just let us say 10, actually it should be 11 because here we want here greater than or equal to n. So let us say n is equal to 11, and we have 1 over n belongs to this this open interval minus r to r, because r is 0.1, so 1 over n is less than 1 over 10 whenever n is greater than 10, right? So whenever n is greater than 10, meaning that if you take capital N to be 11, so then our sequence of points will be in this interval. And it doesn't really matter which r you choose, you can make it smaller and smaller and smaller, yet you will find capital N bigger and bigger and bigger, but finite, after which all the points in the sequence will lie in such an open interval. So this is just an example to illustrate the convergence of sequences. And now let me digress a little bit and ask about the uniqueness of the points where a sequence can converge to. So the question here is if xn is a sequence, can it converge to more than one point? converge to more than one point in X. So this is closely related to the topology, as you can imagine, and this leads us to a very nice property of topological spaces called the Hausdorff property.